Hi everybody, this is about complete topological quantization of higher gauge fields. So I'm currently at the Base Center in Edinburgh at the conference Geometry, Higher Structures and Physics, hosted by the International Center for Mathematical Sciences, which is on the top floor of the Base Center. So tomorrow I'm going to lecture a mini course on this topic of complete topological quantization of higher gauge fields. And tonight, hereby in this video, or maybe in a series of three short videos, I'll do a kind of draft recording of what I'm gonna say. So I have some notes here of essentially the material that I will write to the blackboard tomorrow, and I'm just gonna walk through this and explain a bit what's going on. So you see what's material based on some other stuff. And here's the script. So there's three parts to this presentation. The first is completion of high gauge theories, this first part here. Then I'll talk about the complete topological quantization. The complete is in the sense of that it gives the right quantum observables right away without going through procedures like anomaly cancellation, renormalization, resummation. It gives us the complete topological quantization right away. And finally, I'll speak about actual application to topological quantum materials, so to actual experimentally relevant questions. So there's some predictions actually that follow from this theory here, which are testable in experiment. I don't think I'll in this lecture I won't get to these predictions, but you can find more if you follow the links here. This PDF draft is a expanded lecture notes that has much more detail than, it's still an exposition, but it has much more detail than what I'm presenting now here. So in order of detail, you can start here with this lecture series. Then if you want to know more, you go to these extended lecture notes. And in there you find links to the actual articles that have all the full details and everything. So, all right, so let's get started with part one, completion of high gauge theories. You know, I'll not actually say a priori like what this is going to be. You'll find out in just a second. So what is the motivation for this stuff? So there's an ambitious motivation. So the claim is not that this motivation is necessarily fulfilled in what I'm presenting now, but it's certainly our motivation for doing this. So we want to understand what is the global completion of 11-dimensional supergravity. This goes in the direction of, you know, the completion or the UV completion or whatever of 11-dimensional supergravity is meant to be this mysterious M theory. You know, a quantum gravity, non-perturbative quantum theory underlying possibly theory of everything. Anyway, it's meant to be some completion of 11-dimensional supergravity, and people rarely speak about what it actually means to complete a theory like 11-dimensional supergravity. And what we're going to do is certainly one aspect of what it means, namely the global completion. We'll make global sense of the gauge content of the theory, which may or may not be the full notion of what you want to understand as completion, but we'll see it actually covers a whole lot of ground that is usually or that is traditionally missed. And then also we want to understand the corresponding completion of the M5 brane probes in this. So this sometimes goes, or some limit of this goes by the name theory X. So a lot has been said about that, but few people actually went to the root formula that exists, like the root definitions of what is an M5 brane probe in 11-dimensional supergravity, before I take the decoupling stuff and actually try to think about how to complete that theory globally. Like first of all, before we make all kinds of conjectures about what happens in this 2,0 theory as we take the decoupling limit, let's first have a very careful look at what is the M5 brane theory in the first place. So this is for a single M5 branes, I should say, and yet there is non-abelian effects there once you complete the theory. Anyway, and so then relatedly actually, which is this word relatedly does a lot of work here, we'll find out and we'll see that we actually can say something about fractional quantum Hall anions in certain 2D electron gas or electron liquid systems called fractional quantum Hall systems, which are strongly coupled and thereby actually out of reach of most traditional theory, and yet it's experimentally verified that they host. This has been detected just in the last few years by a few groups though, independently. They host these very interesting solitons, one should really say. They're not fundamental particles, solitons or defects that are anionic. So this goes under the term topological quantum, as in topological quantum computing or topological quantum information theory. And even though people like to speak about it as if everything is known about onions, they're described by some fusion category. These are hypotheses that are not grounded very much. People are working on this, but they hadn't been grounded very much in like microscopic physical derivations. So we're interested in, and then there's effective description of fractional quantum Hall systems, onions, by Chern-Simons theory. If you look at the details of this, there's actually intrinsic tangents in the ansatz of the Chern-Simons ansatz. You need to assume certain things that have to be globally defined for the whole thing to make sense, actually just are locally defined. So there's actually problems with this idea that it's abelian Chern-Simons theory that is the effective theory of onions. So we're after resolving these internal tangents for an effective and maybe beyond effective theory of these onions by asking, well, let's first of all see what does it actually mean to have exotic magnetic flux in this system, because these onions, turns out, this is well known but maybe not fully appreciated, actually carried. They are crucially carried by magnetic flux quanta. These flux quanta induce vortices in the electron gas, and people like to say it's these vortices, these quasi-holes that are the onions, but primarily it's actually the flux quanta, the magnetic flux quanta that cause or that are attached to these vortices, and it's exactly the nature and the exotic nature of flux quanta that what I'm talking about here is all about. Let me actually make the screen a bit larger. Make the type here a bit larger. That was the whole point actually of typing it this way. Okay, so let's get to part one, completion of high gauge theories. So recall, to start with something that is well known, Maxwell's equations in a vacuum. So there's a two form, F2, the Faraday tensor. It's closed. That's one half of Maxwell's equations. And then there's its Hodge star. So the subscript here on the Hodge star indicates that we're in 4 dimensions as usual. So this is ordinary space-time. The Hodge star of F2 in vacuum is also closed. So the Raman differential is also 0. So if there were some electric source, some currents moving around, then on the right side of the second equation we would have the current density 3 form. But we can consider this, but it's, I'm cutting some corners here for this presentation. So let's just look at these vacuum equations. So dF2 is 0 and d star F2 is 0. It's pretty simple, right? But so let's just look what's going on. So surprisingly good idea turns out to rewrite the previous equations, write them in what's called sometimes pre-metric, or it was later rediscovered actually in the string theory literature, and it's called duality symmetric form. Write this as follows. Let's say there's 2 differential forms, and there's 3 equations on them. So one differential form F2 is closed, the other differential form G2, say, is also closed. And then the third equation just says, well, after all, G2 is actually the Hodge star of F2. So this is trivially equivalent to the previous equation. You might think nothing much has happened, but it's a surprisingly good idea, actually, to rewrite things like this. If you want to know more about what's so good about the idea in general, you can follow this link here. But we'll see in a moment, actually, how this, for instance, this entangles right away canonical coordinates and momenta once we actually construct the full phase space of the theory. We're looking here essentially at the avatars of the canonical momenta and coordinates of the field variables, and it's a really good idea to separate them right away. Anyway, we can certainly do it, so we do it. So we take this as our starting point now for the generalization. We want to say we're interested in a higher homotopy, higher structure. Oh, here's a typo. We're interested in higher Maxwell type equations to be formulated on higher flux densities. So I'll write this F with an arrow, which just means it's a tuple of flux densities. F with some index I here. Oh, there's another typo. Okay, I'll fix these typos. So omega is of course denotes the omega dr denotes the set of smooth differential forms. So there's a tuple of these forms in some degrees on our 1 plus d dimensional space-time, an I index tuple. So this just means we'll see examples in a moment. Here we have 2 of these flux densities. Now we just say let's have any tuple, finite tuple, I should say, finite index at I of some degrees. And then the equations of motion are of this form. D of that, so of each item in the tuple is a polynomial of a wedge product polynomial of the others. So P is P with the arrow means an I tuple of graded. So maybe here's another typo. Okay, this is a recurring theme now. So I'll fix these typos after this talk here, after this recording. So P is an I tuple of graded symmetric polynomials. And we also say that similarly that the Hodge star with respect to our space symmetric of each item in the tuple is, a given mu, which is a linear map from, the span of these flux densities, the linear span of them to themselves. Right, so this says, okay, there's some Maxwell equations with nonlinear terms, and here's some self-duality equations among these already duality symmetrized flux densities. So that's what we're going to call higher Maxwell type equations of motion for high gauge fields, or for the flux densities so far. This is the analog of the Maxwell equations. So here's the examples that are motivate this, that you should keep in mind. There's more examples, of course, but these are the ones that are good to keep in mind beyond Maxwell theory. So there's the RR field in type 2A10D supergravity. Similarly, there's of course one in type 2B, but I'll keep writing the one in type 2A, which the tuple is now a tuple of flux densities of differential forms in every even degree. They're all closed, so it very much looks like, at this point, just Maxwell equations sort of in every even degree. But then there's, I don't know, but anyway, there's this duality constraint that says, well, they are pairwise Hodge dual to each other, as you can see here. So that's the famous RR field in 10D. Notice, right, how we're doubling stuff. So this really just means that the original R fields are just those, say, in degrees 2, 4, 6, 2, 4, and then the rest are Hodge duals of them. So if we want to describe a self-dual high gauge fields, which is dual to each other, we use the exact same formulas here, the exact same structure, but we do not do this doubling. So suppose you just have a single in your tuple. There's just, this tuple of f's, vec f, that's just a single h 2 plus k, 2k plus 1 in 4k plus 2 dimensions. And so say it's closed, and then, well, the Hodge star, being a linear isomorphism, has to head up to scale at least, has to say this single flux h 2k plus 1 is self-dual. So this is a self-dual high gauge field. It fits right into this formalism. So by not doubling, we make things self-dual. Then there's Maxwell-Chern-Simons field in, well, it does appear in particular in minimal 5D supergravity. Maybe, you can also consider it outside of 5D supergravity, but it's kind of interesting for other purposes that I'm not going to have time to touch on here in this discussion. To think of it as being the gauge sector, which it is, of minimal 5D supergravity. So we have a two-form flux as in Maxwell theory, it's closed. Then we have now a three-form flux, so that is going to be the Hodge dual of the two-form flux. Since we're now in 5D, take the Hodge star with respect to a 5D metric, so the remaining metric. It's a three-form, and now is the first time that we see such a polynomial self-sourcing term of the fluxes here. So df3 is not 0, but it's proportional. This is more or less conventional at this point. The exact prefactor becomes relevant when you look deeply into the flux quantization that I get to. At this point, it's just any non-zero factor would do here up to isomorphism. So the point is just that it's actually proportional to the other flux squared, wedge squared. So there's kind of a sourcing term. You see, if you remember the original Maxwell equation, on the right-hand side, which I omitted previously, this would have been the electric current. This plays the role of the electric current now in 5D. So this field is self-sourcing. The square of the flux density acts as an electric source for the field itself. So it's a nonlinear equation of motion. And this nonlinearity, we will see, has the effect that as we flux quantize this here later on, it will have to be in what's called non-abelian cohomology theory. So it's not even in, people are fond of describing flux quantization in generalized cohomology theories, but this generalization is that going back to Whitehead, in the sense of generalized homology theories, and these are not actually that general. I mean, they're quite general, but they're actually all abelian in a sense that they're represented by infinite loop spaces. And so we're going to consider, for the reason of these nonlinear couplings here, we're going to consider non-abelian flux quantization laws. That's kind of a big point of what I'm describing here. All right, and then of the same form as this Maxwell-Chern-Simons field in minimal 5D supergravity, there's sort of the higher Maxwell-Chern-Simons field in 11-dimensional supergravity, also commonly known as the C field, which looks structurally the same as before, except for degree shift. So now we're in 11D, there's a 4 flux, which is closed. There's a 7 flux, who is the Ram differential, so which is kind of sourced by the square. Oh, here's another type of this G4, wedge G4. I should have checked this for typos already, right? So I'm working on a bit of a tight time schedule here, since the conference is running, actually. Anyway, so and G7 is the Hodge dual. Okay, so these are the key examples that we're after here, the ones that you should keep in mind. Okay, now we want to look at the solution space of these equations of motion. So we've defined higher Maxwell type equations of motions for higher flux densities. We gave some motivating examples. So now we want to understand the solution space. So for that purpose, let's assume spacetime is globally hyperbolic. So a spacetime is of the form a time factor as a Lorentzian manifold. It factors, or as a metric, as a Riemannian manifold, it factors to the time axis times the spatial part xd, which I listed maybe too many typos here. Anyway, you can read it. So such that xd is the Cauchy surface. It's embedded for any time t, in this first factor here, into this split. So then let's consider the time local solution space. So we're going to write log sol for local solutions. So these are local in time, meaning they exist in a small neighborhood of time around time t. They may not be extendable to infinite time due to singularities that may develop, which we don't know. So they are, technically they're called germs of solutions, defined in some open neighborhood arbitrarily small around t of the above EOMs around this Cauchy surface. So that's so you remember, we're after constructing the actual phase space of the theory. So by a phase space, one really means, even though this is not often made fully manifest, sometimes people speak of the covariant phase space. To make manifest that, the phase space is actually just the space of all solutions of the equations of motion, possibly parametrized by initial value data on a Cauchy surface, and that gives the canonical phase space that is actually mostly presented in textbooks. So we're after exactly that kind of analysis here, and this solution space might already be called the phase space of our field theory, were it not for the fact that we are not actually looking at the full field content of the theory yet. But these flux densities are going to be, as you already know from Maxwell theory, as Dirac discovered, 80 years after Maxwell, the Faraday the flux density of the electromagnetic field is not actually the full field content of the electromagnetic field. There's actually gauge potential, local gauge potentials, that constitute the full field content, and they are subject to some constraint, this flux quantization law. It's only in this totality that we actually have the full globally defined field content of first of Maxwell theory and then of our generalized field theory. So it's only after we first have to complete our flux densities now to full gauge fields, and then find the solution space of these full fields, and that's going to be our phase space. It's going to be a higher stack actually in general, but that's why I'm calling this the solution space at the moment. But you're supposed to think of it as being in the avatar of the phase space. All right, so since we have assumed that we want a globally hyperbolic space-time, what we can do is we can take local solutions and restrict them by pullback. Iota t was a bit scrambled above. Iota t is the embedding of the Cauchy surface, so we can pull back along this embedding, just restrict all our forms on space-time to the Cauchy surface. So that gives us an analogous tuple of forms, which I'm calling B now. It's a tuple, I tuple of forms of the same degrees that we had before. It's the restrictions of all these things. And they certainly satisfy, because pullback commutes with the de Rham differential, they satisfy this equation, this differential equation. D of every item in the tuple is the corresponding polynomial of the other B's. And what the non-trivial content of this, slightly non-trivial content of this proposition is that this is actually an isomorphism that, notice on the left here, we had this kind of differential equation and the Hodge duality constraint, whereas on the right here, there's no further Hodge duality constraint. This is a kind of simple computation. We do this in this article, Flux quantization on phase space. We work, it's an exercise though. You can just check this. What's happening here is that the role of it's kind of the Hodge duality on the left here is actually absorbed in the isomorphism. So on the Cauchy surface, each flux and kind of its dual flux become independent in the same way that canonical coordinates and canonical momenta on a Cauchy surface are independent of each other. And then the fact that they're actually Hodge dual on space-time, sort of when you go away from the Cauchy surface in space-time, that actually encodes how they determine each other's time evolution through space-time, which establishes this isomorphism. So the Hodge duality gets absorbed by the isomorphism, what is left is just a pure cohomological, and that's the key point, just this equation. So this is our reason why it's such a good idea to start with this duality symmetric formulation of higher gauge fields. Because at this step, it gives you immediately the structure of this avatar phase space. We immediately see, anyway, we see what we see here. Right, so I guess I'm saying it on the screen. Dual flux densities become canonical momenta. I'm sort of just claiming this right now. I haven't really shown it yet, but it's kind of plausible if you can already kind of see it. Hodge relative relation disappears, is absorbed in the isomorphism. And the remaining differential relation, right, so this is what in ordinary Maxwell's equations would be called, you know, where you have these two, F2 and G2. And so you have these two relations, which are the Gauss law constraints, the magnetic and electric Gauss law constraints. And so there's a famous fact that if you, in electromagnetism, if you just solve the Gauss law on a Cauchy surface, that is the constraint. You have to set that is the, from constraint canonical quantization, you have to solve this constraint on the Cauchy surface, but then time evolution is determined. And we just found here the very general, or quite general, higher degree generalization of that. All right, so here's the next proposition. So we've just seen, let's see if we can fit this on one screen. We've just seen that the local solution space is equivalent to this kind of space of Gauss law solutions. And now I'm claiming, and so I'm preparing the ground for doing something homotopy theoretic with this, or algebra topological. So we're just going to rephrase just a bit more. We're saying this right-hand side here, it just reappears as the left-hand side here again, is also isomorphic to something. I'm going to explain this. It's also isomorphic to the set. So read this as follows. This is the differential forms on xt on the Cauchy surface with coefficients in some frac A. So this is going to be a Lie algebraic thing, namely it's going to be an L infinity algebra. So I'm claiming that this space of Gauss law solutions is actually naturally understood as being the space of closed in the sense of flat. Some closure condition on L infinity algebra valued forms on xt. So let's understand how this works. For some L infinity algebra, so L infinity is a shorthand or abbreviation for higher, strong homotopy, higher Lie algebra. Since we're talking about higher flux densities, they're associated now with higher structure analogs of Lie algebras called L infinity algebras. And so there's a thing called I call it the characteristic L infinity algebra because it, as you can see, it characterizes the solution space of the given higher flux densities. So in order to understand this equation, let's just recall a bit, or introduce if you haven't seen it before, how finite type connected L infinity algebras work. So if you care to write out the full general definitions of the brackets of higher L infinity algebra, it's a bit of a mouthful and it's kind of tedious to keep track of the signs, but a well-kept public secret is that for finite type L infinity algebras, where the underlying space, if you forget the bracket, the underlying space G is an n-graded vector space which is degree-wise of finite dimension. That's what it means to be finite type. So then things actually simplify in a dual picture grandiosely. They simplify very much in a way that is just exactly suited for the needs of physics. So it turns out an L infinity algebra, which a priori is some graded vector space that we just saw G, equipped with a bunch of brackets. So there's a binary bracket as for ordinary L infinity algebras. For ordinary Lie algebras. There's also a unary bracket that is the differential of a chain complex structure on G. And there's higher arity brackets. And they have to satisfy some higher analog, mixing them all together, of the Jacobi identity. But now what you can do is, since everything is finite degree, let's take the degree-wise dual in the sense of dual vector space of G. So this V it's like a star, but it's the technically correct way to speak of the degree-wise dual. We're not shifting degrees, actually, we're just in each degree of this n-graded vector space passing to the degree-wise linear dual vector space. And we take the graded, this is for Grassmann algebra, the graded Grassmann algebra on that. So elements in degree 0 become degree 1 and intercommute with each other and so forth for the high degree ones. And so this is a graded algebra. It's a graded Grassmann algebra on this degree-wise dual vector space. And we equip this with a differential. So degree plus 1 endomorphism on this graded algebra, which satisfies the graded Leibniz rule and squares to 0. And we define it as follows. So since it satisfies the Leibniz rule, it's going to be defined, fully determined by what it does to the single, to lambda 1, to single copies of our generators. And on that, we can define it to be the linear, to the sum of the linear dual maps of all these brackets, just sum them all together and take the actual, in the sense of dual maps as you have them. Like if you have a map between vector space, you can dualize to get a map between dual vector space. That's what this means. Right, so the bracket, the binary bracket goes from 2 copies of G to 1 copy of G. So the dual map goes from 1 copy of G dual to 2 wedge copies of G dual. So it's the differential, the co-binary part of the differential one here. So anyway, so this is a standard formula. And turns out, this is a kind of deep fact, has to do with causal duality of the Lie operand against the commutative operand. So this construction gives, so this is all hidden in this arrow here, this construction is a fully faithful embedding of categories. So that means that everything you can do and know about L infinity algebras on the left is actually preserved under this construction on the right. You lose nothing. You remember exactly everything. So you can just as well equivalently understand L infinity algebras as being differential graded commutative algebras that happen to be of this particular form, that the underlying graded algebra is what's sometimes called, is free as a graded algebra, so the whole thing is sometimes called a semi-free differential algebra. If you have a background in supergravity, you may recognize this as what's sometimes called the geometric approach to supergravity. It's called an FDA, which is a misnomer shorthand for free differential algebra. So these are crucially not free. The differential is not free, otherwise it would be all trivial. But they're free as graded algebras. Okay, so these are L infinity algebras, and actually in this note here, I'm not, for time reasons, I'm not going through examples of this. We'll see one class of examples in a moment, but you want to see some examples of this if you haven't seen this before. For this, go to my notes that I linked to above, and you'll see more. So then, anyway, once you have such a L infinity algebra, and we call this, I also should add this here, we call this the Chevalley-Eilenberg algebra. This DGC algebra is called the Chevalley-Eilenberg algebra CE of the L infinity algebra. And so then we can speak about closed L infinity algebra valid forms. This is kind of a tautological thing. If you see it for the first time, it may seem a bit mysterious, but yeah, this is actually this is the way to go. So these closed or flat are used synonymously. G-valid differential forms are equivalently the DG algebra homomorphisms from the Chevalley-Eilenberg algebra to the DG algebra, the Drama algebra on our space X. So you can roughly see how it goes. It takes every element in G has to go to a form of the same degree, and then since this home here has to respect the differentials, so that tells you that on these differential forms have to satisfy certain differential relations, and these are exactly the kind of differential relations we have been looking at. It says D of all these forms is some polynomial in the other forms. All right, so here's our class of examples. This, even though it's ancient math now, dating from the 1960s, ancient in that sense, I don't think this is fully appreciated widely still in the physics community, or even in the math physics community sometimes. Anyway, so turns out here's the following. Let's consider a topological space. So now we're entering the realm of algebraic topology. This was all algebraic so far, or differential algebraic. Now we're looking at an actual topological space called curly A. So this is different from our spacetimes. This is like an abstract topological space. This would be our classifying space for the charges of our theory. We'll see examples, but some topological space curly A. And for simplicity, I'll assume it to be connected and have a abelian fundamental group. This is a bit more than we really need to assume, but this is a good assumption for this discussion here. And it being of finite type means, here's again a missing bracket of course, means that all its real cohomology, or the rational cohomology equivalently, is finite dimensional in every degree. That means it's finite type. It's a space. Then there's something called its real Whitehead L infinity algebra. I call it Mathfrak LA, so LA. So how's it defined? It's, the underlying graded vector space is the space of rationalized homotopy groups of the loop space of A. So it's connected, so there's makes sense to speak of the loop space of A here, at any base point in that one connected component. We can form the homotopy groups of that, the higher homotopy groups, and then tensor them as abelian groups, right, by our assumption that tensor them with R. So this gives us vector spaces spanned by the generators, the non-torsion generators at this point. So this tensor product forgets It's called the torsion in the homotopy groups. All finite pieces of homotopy groups, finite direct sums, disappear under this tensor product, and only the copies of Z, whenever there is a copy of the integers in these homotopy groups, gets turned into a copy of R. This is what we remember. So this is what our underlying underlying chain complex is. And so the brackets are, on this weighted L-infinity algebra, implicitly defined. The brackets, remember, define the differential on the dual CE algebra. And we require that the cochain cohomology of the CE algebra is a cochain complex with that differential, that cohomology is actually the real cohomology for our space. Turns out, that's why it's a definition / proposition. Turns out this is Sullivan's big theorem for the foundation of this. This is why these C algebras LA are called Sullivan models or minimal Sullivan models. The theorem is that this determines the brackets and the brackets up to unique isomorphism, up to isomorphism. So this is the weighted L-infinity algebra LA. And this is known as a rational model, the G algebraic rational model of our space. Turns out, in a precise sense, for which which one can make precise, this L-infinity algebra captures the rational homotopy type of A completely. So it knows everything about sort of the non-torsion part of A, that which remains. So all torsion in the sense of torsion subgroups is killed. So here's an example. I'm just stating these examples now. So we wrote this book called The Character Map in Non-Abelian Cohomology, where you should go to the NLab page for it to find the actual published version. Don't go to the archive version, which is not the latest one. The Character Map in Non-Abelian Cohomology, which walks through these examples. But these are classical examples, but in that book we review everything and develop the theory that I'm referring to here. Excuse me. So the examples, sorry, let me just get a drink here. All right, so for electromagnetism, turns out, remember, so we claimed that this solution space is isomorphic to the space of flat Math-Frag A-valued differential forms on a Cauchy surface. And so the question was, so which of these higher Flux, higher Maxwell equations is now characterized by which L-infinity algebra? So it turns out, for electromagnetism, it's the weighted L-infinity algebra of the classifying space of U1, of the U1 gauge field, squared. The reason that we have squared here, so it's two copies of the classifying space, is that in this duality symmetric formulation we actually see very manifestly that as we flux quantize, since we're actually flux quantizing on phase space, we want to be flux quantizing both the electric and the magnetic fluxes. Whereas often in the literature, and this is kind of what I want to get beyond here, often in the literature people behave as if it's sufficient to quantize the magnetic fluxes. But no, when you're on phase space, and in particular when there's this nonlinearity in the Gauss laws, which mixes the electric and magnetic fluxes, then it makes no sense to just quantize one of them. You have to choose how to quantize both. And that's why we see two copies here. So in electromagnetism, we see that there's an L-infinity algebra which kind of comes from which remembers that there's two charges of degree 2, or two flux densities of degree 2, electric and magnetic. For the self-dual high gauge field, this collapses to a single copy. And so I'm switching now here from so BU1 is also the same as B2Z. So I'm writing it here as B2KZ. Maybe this is a bit... Anyways, this is essentially the same kind of classifying space. The whole point is just that for the self-dual theory, there's just a single copy of this classifying space instead of two of them. That makes it self-dual, like the electric and magnetic notion fuses into a single thing. So then for the RR field, turns out our L-infinity algebra is the weighted L-infinity algebra of the classifying space of the... So U here is the stable unitary group, the union of all UNs, of all finite rank unitary groups, BU. So the full classifying space for K theory is BU times Z, which is not connected, so since I assume for simplicity that we're connected. So this is sort of a classifying space, if you wish, for reduced K theory. Anyway, you can just, it's easy to actually go beyond this assumption that I made, that the classifying space has to be connected. I just wanted to get distracted here for these lectures with that issue. So BU is up to some connected components here, is the classifying space, sometimes called KU0, is a classifying space for complex K-theory. And of that, we see for the moment just the Whitehead L-infinity algebra. So we don't know yet that K-theory plays a role here for the RR field, but we see the rational shadow of that. And so BU just has homotopy groups Z in every second degree. So this L-infinity algebra LBU still looks pretty much like the previous examples, just with more degrees. It just has a single generator which is closed, or which has trivial brackets in every second degree. So it's still not non-abelian. But now something really crucial happens as we look at our other two running examples, Maxwell-Simons theory and the C-field. They have nonlinear classifying spaces. Well, at the moment we're just looking at Whitehead L-infinity algebra. So just to claim it, you see it here, the Whitehead L-infinity algebra that characterizes the Bianchi identities and Gauss laws of Maxwell-Simons field at 5D is that of the 2-sphere, and for the C field in 11-dimensional group gravity is that of the 4-sphere. So this is actually a simple fact in rational homotopy theory, given what I said. I'm just going to just throwing it at you at the moment, just drops from the sky. So if you want to see derivations of this, check out the top of these lectures, the links where everything is discussed in full detail. All right, so here's another typo. All right. So now that we've identified that the flux densities, their equations of motion, are characterized by an L-infinity algebra that is a rational shadow of a space, the most natural thing is to actually bring that space, or a choice of that space, into the game. So for that purpose, let's first say that the total flux of a flux density vector F, so of a tubular flux density, is its image in non-abelian de Rham cohomology, which is the concordance classes of these closed forms. So let's try to understand this. I should have included a picture of this in my notes. In the PDF notes, I have a picture of this here. So remember, we said on a fixed Cauchy surface, the fields satisfying the Gauss laws are these closed A-valued differential forms. But now you might choose another Cauchy surface, and then say at some later time. But then we know that in between, like there's an interpolation between these flux densities. That at the earlier, both of them are restrictions of an actual solution or of space-time, which is also a closed A-valued differential form, but now in space-time. So concordance is such an interpolation between differential form data. If you have differential form data on some surface, then a concordance means you have extended the differential form data with its closure conditions to the cylinder, to a cylinder over that surface, such that on the other end of the cylinder it restricts to some other value, and then you say the values at these two ends of the cylinder are concordant to each other. And quotienting out that equivalence relation is what we're going to do here, and that quotient we call the non-abelian de Rham cohomology, H1 de Rham of X with coefficients in A. So it's called this way because if A happens to be a line, if A happens to be abelian as an L-infinity algebra, and that it's Whitehead L-infinity algebra of some BNZ, or some BNQ or whatever, so then actually this relation, this brings us back to ordinary de Rham cohomology in degree n for BNZ. So this is an actual generalization of ordinary, which I would call now abelian de Rham cohomology, to this non-abelian case where everything is coefficients in this L-infinity algebra. And okay, so here comes the big point now. This is the title of where we have this book called the Character Map in Non-Abelian Cohomology. This now tells us that there's actually a map that compares these charges that tells us how to get this total flux in non-abelian de Rham cohomology from something that has torsion information, that has more information than was present in the differential forms. So use some notation here. So this L upper Q is called the rationalization of A. So there's this method of taking a space and approximating, of kind of forgetting its torsion information. Now, I'm not going to say more about this at this point here. And there's a real version of this, and there's a comparison map. Another typo here, from space to its rationalization, its real rationalization. And so from that we can form the following diagram. So we want to say on the left, so on the right first of all is what we just introduced. We have the non-abelian de Rham cohomology with coefficients in A. It turns out there is something called a non-abelian de Rham theorem, which we prove in this book, the character map in non-abelian cohomology. An analogy to the de Rham theorem, which says that de Rham cohomology is isomorphic to real cohomology of manifolds. We see here that this non-abelian de Rham cohomology is actually isomorphic to maps into this realified classifying space, connected components of that. More generally, we say that maps into any classifying space, assumed to be connected, remember? Connected components of this we're calling the non-abelian cohomology of X with coefficients in the loop group of A. It's actually the loop infinity group of A. So this is just notation, which has its purpose and its reason, but for the moment it's just notation for exactly this, just homotopy classes of maps into this classifying space. And so down here now, since in both cases we're just mapping into A, and we have this map from A to its realification, we can kind of push forward along this, and so we get a canonical. Why doesn't the blue go away? Why does this happen? Sorry, just a moment. All right. So down here there's a canonical map that takes this connected components of mapping spaces to this simply by post-composing with this comparison map. But then we can interpret this as a map from the non-abelian cohomology to the non-abelian derived cohomology by these isomorphisms and equivalences. And that's called the character. Why is it called the character? Because it reduces, maybe I haven't even stated this here. I should maybe add this. This is called the character because if you take A to be K, the classifying space for K theory, this becomes an extra Chern character on K theory. If you take A to be B and Z, this becomes the Ram homomorphism from integral cohomology to the Ram cohomology. So in this sense, it's the generalization of the character map that you know from at least K theory. So then, right, so we know we've seen that the total flux of our higher flux densities lives in this non-abelian Ram cohomology, but we now see that this actually receives this map from something that is, in a sense, finer. It's integral in a sense. So that from an actual cohomology theory, which is not realified. So this allows us now to say a flux quantization of our gauge theory is a choice of such a space A, which has to be admissible in that its weighted L-infinity algebra has to equal or be isomorphic to our characteristic L-infinity algebra, which I'm tacitly using here. And then we can say, okay, a flux quantized gauge flux density, a quantized tuple of flux densities F, back F, is now, well, let's adjoin a charge for it, chi, and let's demand that the image of the flux densities so its total flux density is actually the character image of that charge. You see, this constrains the flux density such that the total flux cannot be anything anymore. The total flux has to be such that it's actually potentially the total flux that is sourced by an actual charge, where what an actual charge is determined by this choice of A, which is not fixed. It's just constrained by this condition here. And we'll see this in a moment. So you have to choose A to complete your theory, but once you've chosen it, you know what the charges are, and then you can say, well, the admissible quantized flux densities are those whose total flux is actually the character image of a charge. So there's either none or infinitely many admissible A. So choosing A is a hypothesis about the correct model for the given physics. If you think the physics is determined, like, if you're not just playing around, but like with Maxwell theory, there's the electromagnetic field in the actual real world, and you can make measurements about it, and you want to figure out what is the actual mathematical description of it, then choosing A is a hypothesis about what describes the physics. It's a choice of model, and you'd say, well, that is my correct choice of models. We're finding here that choosing A completes your theory, and so you have to make the further choices that you had already started to make when you picked the non-complete part of your theory. Right, so the examples are direct charge quantization of the electromagnetic field. The sort of traditional choice, ever since Dirac, the 1930s, is to take A to be B1. This is, even though everybody accepts this as it's set in stone, this is not actually unique. There's other flux quantization laws that are consistent, and we could talk about this, but I don't do it here. And if you look at what the actual evidence, the experimental evidence is, there is experimental evidence. It's not actually from monopoles, as people always say. It's from Abrikosov vortices. I don't have this in these notes, I think. But Abrikosov vortices in type 2A superconductors are quantized in the integers. There's an integer number of them. And from that, one can actually determine that the space, the magnetic classifying space, has to be B1 times something that is torsion which vanishes on the 2-sphere. So even that doesn't fully determine. So I'm just highlighting it to indicate that even though everybody speaks or people like to speak as if direct charge quantization is set in stone, it's actually also a hypothesis that hasn't been fully checked yet in experiment. That in the duality symmetric form that I'm displaying here, it's actually BU1 for the magnetic and for the electric charge sector. Well, then there's something which I like to call hypothesis K, even though nobody else currently calls it that, for the R field. This is the famous hypothesis that de Broglie charge is in K theory, and that the R fluxes are in the corresponding other K theory. I'm calling it hypothesis K to indicate that that too, of course, this famous topic from string theory from the 90s, is a hypothesis which, even if you buy the arguments for it, which are somewhat shaky, that K theory has something to do with it. There's still choices there which haven't really been fully sorted out. So the assumption, it's a very natural assumption that the R field is in just K theory. But this is a long topic. We could talk about what the loopholes are and what other possible choices would be. Anyway, it's a hypothesis. I'm going to call it hypothesis K. The R field is in K theory. Flux quantities in K theory. Remember, its characteristic L-infinity algebra was LBU, and so this hypothesis says, well, then the classifying space is probably BU, or BU times C. That's the classifying space for complex topological K theory. And so then, this way we can make further hypotheses. So just we give them names in order to be able to refer to them. So for Maxwell-Simons field, remember, the correct L-infinity algebra was the weighted L-infinity algebra of the two-sphere. And you see I've already labeled all these weighted L-infinity algebras by the space that I end up choosing now. But it's kind of the minimal choice, actually. It is the minimal choice as far as cells of CW complexes go. So hypothesis lowercase h on the Maxwell-Simons field says, in some sense of right, this is the right flux quantization law. Take the classifying space to be the two-sphere. Could be the two-sphere times the classifying space of some finite group, or could be some more fancy things. So this is not singled out, but it's a natural minimal choice. And by the same token, you can take the classifying space for the C field in 11-dimensional supergravity to be the four-sphere. And so the classifying space, the commodity theory they classify are called co-homotopy. Since instead of mapping out of a sphere, which is called homotopy, we're now mapping into a sphere. It's co-homotopy. So K theory and co-homotopy are generalized non-abelian commodity theories. And so we call this hypothesis capital H for homotopy on the C field. So these are assumptions for what the global flux quantized version of these gauge fields actually are. So this is not the end of the story, but I will be very schematic here for the purpose of this recording and this talk concerning the full step. So this is not actually, so just the choice of A and the choice of such a charge is not yet the full completion. So it's not true that the completed gauge field is just the flux density and the choice of charge. That is part of it, but there's still one part missing, the gauge potential. And the issue, you can see it here we're imposing an equality between total flux and the character of the charge. And since we're in high gauge theories, this is not the right thing to do. You don't want to impose an equality. What you do want to choose a homotopy. You want to choose, if you wish, a gauge equivalence, a gauge transformation, which witnesses this equality of charges. And that is one further degree of information. So in order to make this precise, one needs to talk about geometric homotopy theory, also known as infinity topos theory, or stack theory. So I'm not going to do this here. This is just a schematic point here, but again, you find all the details and more that you want to see in the notes that I've linked. So the full completed high gauge field is actually not just the flux density and the charge, but it's not just the equality, but it's actually a gauge transformation homotopy, which I'm going to write head A, which exhibits this equality. And that turns out to be the gauge potential. So the globally completed phase space is schematically, phase space is the space of triples. The gauge, this is really a bad typo now, the flux densities. Okay, I'm going to fix all these typos now after this recording. Sorry for the trouble. Anyway, so these are the flux densities. The triple consists of the flux densities, the charges, and I'm glossing over some technical detail here, but essentially the gauge potentials are homotopies or gauge transformations between the flux densities and the charges. Of course, you have to ask, well, where does this take place? A priori, they don't live in the same space, so it's a homotopy between them in the correct space that we in our encyclopedia article, we call it the how do we call it? The modular space of deformations of flux. Anyway, so there's some, you can make this precise in this. And then it turns out this is the correct, if you apply this to electromagnetism, you see here's the Faraday tensor, then you get the integer or an element in integral cohomology being the charge. And these gauge potentials, and this is a non-trivial statement, come out to be the actual local one-form fields, glued on patches to form a connection or a U1 principal bundle that you're used to seeing. So it's not evident from this description that this comes out as kind of a piece of magic that it does work. So in full detail, this space here of triples is actually a smooth infinity group order at higher stack, which is such as the homotopy pullback of the character map from total flux to flux densities. So that's essentially. I'm not going to go into this because next, actually, we're just interested in the topological observers on the system. It turns out the topological observers don't see most of the structure. So this structure is clearly very important for the full theory, but topologically, it turns out that in a way only the charges actually remain visible here. You still need this whole story to understand where these charges take their use, namely in A cohomology, in non-abelian cohomology with coefficients in omega A. But it turns out the gauge potentials actually drop out, sort of are not visible to the topological observables beyond the charges that they induce. So we actually don't have to care too much about the actual technical definition of this space. And so essentially, in the following we will only need the shape, what I call the shape of the phase space. So another typo, space is phase space, which turns out to be given by a concrete formula. And that will be the topic of part 2. And I'll stop here. I maybe just scroll back to remind you where to find details of this stuff. So this is the title here. So if you Google for either the talk title, Complete Topological Quantization of High Gauge Fields, or go to this webpage, the website, ncatlab.org/Schreiber/show/ICMS25. You find pointers first to the expanded lecture notes, and they have pointers to all the details and more. All right, so more in part 2.